My name is Suman Bhattacharya. I am a DS lead at Uber. Currently, I work for a team that looks into safety issues at Uber, and we build data science model around that. Previously, I have also built experimentation platform at Uber. So today, I'm going to essentially continue where Deba had stopped, which is why he was explaining why the anomaly detection is important. And I'm just going to get into the how part now. So at the heart of any anomaly detection, there is a imbalanced data. So if you think about it, if you take an example, let's say credit card fraud, uh, the number of fraud is always going to be uh, relatively small compared to the not fraud case. So we are always going to deal with this imbalanced data. And here is an example from Kaggle, where they outsourced they open source this credit card transactions data. And so if we look into this data a bit more, and it is available online, by the way, there are about 492 frauds out of some 300,000 transactions. And they give a bunch of features, and the goal is to basically classify fraud versus not fraud. Um, so um, now the question is how to handle this imbalanced data, which is at the heart of any anomaly detection problem. There are two ways to think about it. One is we have to choose the right metric, and I will get into the details of the type of metrics we choose to determine the accuracy of the model. Examples include area under the curve, or F-score, or area under the precision recall curve, etc. And the next bucket to think about is what sampling technique I want to use for to essentially over sample the minority class or undersample the majority class. So we have to so that we end up with a balanced data set. And as we know that a balanced data set makes most of the machine learning model more accurate. So that's the motivation here. So now on the metric side, on the left-hand side, um, this plot here is the typical AUC plot that we see in most machine learning model. This dotted line is, or imagine that we are just flipping a coin and making a decision. And this line would be if we come up with a better model than that. You can see that from no skill classifier, this skill classifier differentiate, but it's maybe there is room for more improvement. If you look at this plot, this is similar to the left plot, except that this is a plot under precision recall. This is the area under the curve on the precision recall plot. So the no skill curve dotted line is here. And we can always end up with a model worse than that, but this is our skillful classifier. So you can see that the differentiation is much more. Other than that, there are other scores we can look at, namely F-score, which kind of provide a balance between precision recall curve. So one way to think about F-score is how do I translate this curve into one score so that I can compare. Another one to think about is Breer score, which basically it's like mean square error between the expected and true probabilities. So instead of looking at the labels, we are looking at the probabilities. So when you're dealing with imbalanced data set, the one like the one that I just showed in the previous slide, is better to measure your model using AUCPR, which is this plot. If your data set is somewhat imbalanced, but maybe 80-20 case, then you can use AUC or AUC-PR. But for imbalanced data set, AUC-PR provides a better way to look into this accuracy of this model. So now getting to the sampling strategies, here is a code snippet. Basically, we have two choices. One is we can upsample the minority class, or we can downsample the majority class. Whatever we are trying to do, the way to do this is first we take our data set and we distinguish the not fraud and the fraud, and then we can upsample the minority class, which is fraud. Or we can, so for upsampling, what we're doing here is we are sampling with replacement, and or we can, downsample the majority class, which is again just similar to the minority class, but it's sampling without replacement. A bit more sophisticated technique is something called SMOTE. The full form of SMOTE is synthetic minority oversampling technique. Okay, and I will explain what that is. So essentially, what SMOTE is doing is it's based on the nearest neighbor idea. So we have these black dot points, which represents the minority class. And what SMOTE does is it finds the nearest neighbor of these black dots and try to generate these red points along this line. So, and there are several variants of SMOTE that people have worked out. For example, adaptive synthesis is where it assigns sort of weights to each one of these points. And let's say that this is our original data from the credit card fraud. So the blue points are the majority class and the orange ones are the minority class. And if we use SMOTE, then we'll end up with a generated sample that looks like this, because it's connecting along the lines of the point that connects the points. So it looks like this. Another upcoming area, I would say, in terms of generating or how to generate minority class is leveraging generative adversarial model. Now, generative adversarial model is something that has been used in the space of image synthesis quite a bit. The primary use looks like you start with some random noise, you add some random noise to your neural net, and you feed that noise to your image. So let's say this is my actual image, and this is what the GAN would synthesize. And then what generative adversarial model does is it connects, it computes the loss between these two images and try to minimize that loss. But there is nothing in GAN that restricts its usage just to image data. You can use it for general data as well. So one way to think about how to use GANs for, say, something like credit card fraud data is we use GAN to generate the minority class that I was showing before. And what it will do is it will generate synthetic data that will look almost like the real data of the minority class by minimizing the loss. So we start again with a random noise, and we start with some sample, and it goes through the layers in the generative adversarial model, and the discriminator layer would differentiate between the real data and the generated data and try to minimize the loss. So I would stop here, and with that, we can go to the Q&A part of our presentation.
Yeah, so now, you can ask questions. If you have any questions, please post your questions on the chat box and we will answer those questions. Okay, I have a question for related to anomaly detection. Why it is becoming so important nowadays? I mean, I am getting a lot of queries from the industry to figure out some techniques to, is this going to be a very important problem?
I can take a very quick stab at the questions. The reason is that there is a deluge of data. So it is because there is so much data these days that it is not possible to detect the right from the wrong very easily. So you would like to understand what is the outliers in your system, and so that you can meaningfully figure out what is going wrong in the system. That is the reason it is becoming more and more. So even collections that would happen at minute interval now are being data being collected at every second. So you could see how quickly there is a or maybe sub-second. So how quickly there is, and how many times that data volume has increased in the last few years, maybe in the last couple of years. So I think as the data volume increases, there is going to be, in every space of the industry, there will be more and more necessity for detecting outliers through anomaly detection.
Okay, I have a question for, there is a question about anomaly detection. Maybe Suman can answer this question. Is anomaly detection handled better using unsupervised or supervised learning?
Yeah, so that's actually a good question. So I would say, in any anomaly detection or any problem, if we have labeled data, then that is always going to produce better accuracy for the model. Now, the challenge with anomaly detection is often we do not have the labeled data. So for that, sometimes we have to resort to unsupervised way of doing it. But in practice, what happens is there is always some human in the loop, whether it's credit card fraud or some other types of fraud or some other anomalies where we get some type of labeling. Given that, we can do some, weekly, it's called weak supervised learning, where we have some label data, but um, it can be useful to do the get to the anomalies.
So it is like a semi-supervised learning. Are you talking about semi-supervised learning? Kind of lots of
Yeah.
unlabeled data with bunch of labeled data, right?
Yes.
Okay. There is another question. I think a GAN example given falls under supervised or unsupervised learning. The
Yes.
example that
GAN is definitely, you need label data to essentially let the network discriminate between the labeled and the synthetic data. So you need the true data points. Yeah.
Okay, there is a question, Professor Vemuri. Can you give your perspective about AI accelerators? Is it mainstream? What is the future of this technique?
Okay, the idea of using an accelerator is not new. Way back in the early days of computing, when we were doing floating point operations, we used to have special chips called floating point accelerators. So anytime we have a compute intensive activity, and if there is a hardware support to perform that kind of a function, accelerator can play a role. And with the graphic chips that are coming, particularly from NVIDIA, it is quite possible that they will have some specialized chips dedicated to the types of operations that machine learning and AI will do. So they will have a role. And actually, right now, many of the deep learning systems are using graphic chips. So in a way, they're accelerators. So they do have a role. I don't know to what extent this trend will continue, but it has been there ever since computing came into existence, so it will continue to be there.
I just want to make a comment about a new chip that is Google is promoting, TPU, Tensor Processing Unit. So that is a AI-based chip, right? That chip is dedicated for machine learning applications. And I don't know whether this is related to this, but I know they are putting a lot of effort in promoting TPU.
Yeah, one can make a hair splitting distinction between that kind of chips and accelerators. Accelerators are typically used for a very, in a narrow sense,
Okay.
to do a very particular kind of a job, whereas the kind of things you are talking about are generic chips to do things faster in parallel.
Okay.
Okay. But yeah, you can call it an accelerator if you want to.
Okay. There is another question. In GAN or SMOT, is there a possibility that the generated synthetic data may be misleading?
Yes. So basically, SMOTE and GAN, work under some assumptions. So SMOTE is doing basically this nearest neighbor thing. So, generally speaking, extrapolation is not going to look, is not going to work here. What I mean by that is because these are rare events do not always capture the full distribution of the data points. So there can be data points that are outside these events that we are seeing. And SMOTE or GAN can only generate something that they are seeing. So it is the unseen data point that will cause error or the limitation.
Okay. There is another question. This is to all of you. Could you share your insights on explainable AI? How advanced is the field in terms of industry applications?
Okay, I probably will give a shot, but anyone probably can answer this question. Right from the early days of neural nets, a challenging issue is a neural net can make a good prediction, but we will never be able to explain how the prediction is being made. That means we never succeeded in interpreting the weights of the neural net in terms of something that we can relate to. So it was always a black box. So if we try to bring that technology into deep learning kind of thing, we are facing the same problem. The deep learning networks are also making good predictions, but we are not able to explain the meaning of these weights. There is some effort, some success, because what we are doing is at the hidden layers, we are interpreting those activations of the hidden layers as features. Like maybe the first hidden layer explains features like edges. The second hidden layer explains features like components of a face, like eyes, nose, ears, and so forth. And at the third layer, we are going to compose the whole thing into a total image. But that is particular to a image processing context. But if you want to do the same thing in general for any type of AI activity, we may have difficulty doing it, but eventually we'll get there. Right now, we are not there yet.
Okay. Any other thoughts on this question? I have other questions.
I can give my 2 cents here. So explainable AI lately is becoming important in the self-driving space, because what happens is when we go through all these scenarios where self-driving can fail, um, we need to understand why a certain thing is in a certain scenario, the self-driving is failing, and that's where the causality connection comes into play, or we need to explain why that particular algorithm has failed. So for example, let's say a cat came in front of the car, and maybe 95% of the time it can detect it, but 5% of the time it cannot, and we care about that 5%. So it's not as easy as like oh, this algorithm cannot detect cat. No, it can, 95% of the time. But the question is, 5% of the time, maybe under some scenario, maybe it's raining and the cat is coming in front of the car, so it cannot detect. So there are all these external variables that comes into play.
Mm-hmm.
And explainable AI has this practical application in the definitely in the field of self-driving technology.
Okay. I have a question for Deba. Deba, you mentioned about anomaly detection in the context of business. Can you give us some other examples that are also quite important as far as making business decisions using data science?
Well, today, the way we, there are different business models that operate. I mean, I'm talking about mainly the online e-commerce businesses. In there, there is a huge application of recommendation engines.
Correct.
Specifically, you look at Netflix, you see all the movies that are what you are going to watch next is determined by not just what you have watched in the past, but sort of similar demographics or similar types of genres that exist. And then your let's say Amazon, where what you bought or what sort of your buying history, or they run a lot of different recommendation algorithms to basically predict or suggest things that can sort of increase their basket size. The other application that I see there are I mean, I would like to tell you a difference here. The similar situation is in YouTube as well. YouTube wants to increase your viewership or viewing time so that they can show you more ads. So there is also a type of recommendation algorithm that runs behind the scenes. On the other hand, Netflix wants to give you the engagement pleasure. They are not optimizing for viewing time, but for the experience that you want to get. So even though they are using recommendation engines, but they are using it for different types of end goals. So I think this is a good example of recommendation is another way of how data science is being used in the business world.
Okay, thank you. And there are a few more questions. One question is, deep neural nets seem to be very promising. Are there new techniques that are showing more promise? That is one question. Anybody can answer this question.
Okay, let me give a shot at this, and then other people can chime in. There are other types of deep networks like recurrent neural networks. That means on the top of a deep network, you can add some of these features so that you can develop models for things like time series. Modeling time series are involving dependence of time. Those things are already fairly popular. So that is one direction in which there are some specialized elements that are being designed in the context of deep networks for that. And whether they are showing more promise than the classical networks, yes, in the sense, like for example, Julia Pearl's probabilistic networks. We can develop deep networks based on those things, and they're extremely popular also. So the basic idea of deep networks is being extended to a variety of applications, including probabilistic networks, reinforcement learning, and so on and so forth. You simply have to dig up into the literature to see where people are trying to apply these things. There is a related question on the next thing. Let me try to answer that also, then I can move on. For the deep networks, what is the example? Feature extraction. You see, the number of layers that you need, if there is no particular formula or rule, you simply have to look at the problem and play around with the number of layers. Maybe 2 or 3 layers are adequate, but there are some deep networks with as many as 10 layers. One of the earliest deep networks was called neocognitron that had 9 layers. So there is no particular rule. These are all what are called hyperparameters. You tune these things depending on the problem. I will let other people tackle these questions.
Yeah. Suman, you want to say something?
Yeah, so if we think about last few years, major advances and milestones. So on the computer vision side of things, Transformer and ResNet. People can Google these things, but just at a high level, ResNet, what that is doing is it's skipping the layers within the deep learning net to avoid the vanishing gradient problem. On the NLP side, there is BERT, B-E-R-T, which is bidirectional encoding representation. That has actually created better NLP model from Q&A to like Q&A type work to translation type work. So much so that one of the major update to Google search in like a decade has been the inclusion of BERT in their search system. So that's how influential it has been. So yeah, these are the few things that comes at the top of my mind.
Okay. Last question before we are almost running out of time. Has there been progress in commercially utilizing quantum computing for AI and or data science?
Okay, I will give a stab at this, and again, others can chime in later. Quantum computing is relatively new, and the only 2 companies that claim to have working models of quantum computing are Google and IBM. And they are making their facilities available in the cloud. If you are a legitimate user, you can try them, but they are still in an experimental stage, and I haven't seen anybody using a killer application to demonstrate these things. It is at an extremely early stage. Maybe in the next couple of years, we will know how successful these ideas are.
Yeah, just I want to say that in quantum computing, so unless they have designed a quantum computer with several hundreds of qubits, we are not there yet. Okay, so I think we are running out of time, and thank you all for joining us today. And thank you, Professor Vemuri, thank you, Deba, and thank you, Suman, for your time and your presentations.